Computer. All right. Hi, people at home.
Thank you for coming. All right, so Matt Christie, who is one of the members of our steering committee and one of the Upper Valley's foremost experts on energy efficiency, in my opinion, is our presenter tonight. Let's see, I'll start off. I'm Ethan Cole, First Chair Construction, based in Lebanon, New Hampshire.
Nick Joeli, architect at Make Architects.
If we could get everybody to just speak up, so hopefully the map will pick you guys up. Thanks, Nick.
Haynes, retired, construction, real estate development.
Eric Francis, White River, I'm just interested in building projects.
I'm Brandon Smith. I work at First Chair Construction with Ethan, doing project management stuff.
I'm Judy Payne. I live in Hanover. This kind of information.
And I'm Paul Gerke. I'm just been and when I can.
I'm Mary Maxfield. I'm interested in making my heating system more efficient.
Tim Mello, homeowner, West Windsor, one, same thing. Interested in heating system.
Dana Clausen, I'm the environmental sustainability coordinator for the town of Hartford, and I was a HERS rater in my previous life.
Richard Ackerman from Norwich. Ross Lincombe, owner of Sage Home, builder in Bethlehem.
Richard Thompson, Cornish, and I'm a retired timber framer, but I'm now my retirement working with our energy.
Travis Filio, I'm from Vermont. I work here in Lebanon with this chair, doing carpentry and sort of specializing in the new ventilation department. And in my free time, I geek out about generative engineering and really big scales.
Daniel Jackson, interested and also have a one-man carpentry business that I'm just starting up.
Mike Vecchiarelli, I'm a lifelong learner and educator and working facility services. Interested in learning more. I'm Tim, I'm an architect based in Meriden, New Hampshire, Tennessee architecture.
I'm Florence. I'm a pediatrician, but there's always you need to learn. Always.
All right, cool. And I'm Matt Christie. Thank you for being here. Appreciate everyone. Here comes Marcus. We'll let him say hi. Yeah, or we won't. Just time to say hi and say who you are and why you're here.
I'm Marcus. I work at Dartmouth College. We're working on a geo exchange system.
Not quite getting that far because what I'm talking about is ground source for residential, small commercial applications. So, all right. So I'm Matt Christie. I work for a company called TRC. We consult with utilities and government agencies about energy efficiency and decarbonization policy stuff. So think Efficiency Vermont running incentive programs to get people to buy better windows, better air conditioning, better whatever. We design and run those programs. We also do research behind those programs to decide what goes forward and decide what the savings claim is for various widgets or measures, energy measures. We, across the board, we also do measurement and evaluation to confirm what the savings are, what's happening with energy. My niche, my bailiwick has been residential energy efficiency and decarbonization for the last 15 years. I'm a director at TRC, and I run a whole suite of programs that are all about accelerating the adoption of heat pumps right now. In my former history, I was an energy auditor. I did a lot more of like the, in the attics, in the basements, understanding all the basics to bring the load down, to bring the efficiency to where it needs to be. And in the last 5 years, my career has pivoted a lot more towards the heating and cooling systems and decarbonizing the end uses that we have. And finding ways to do that and break down the barriers and, promote the efficiencies, make sure that these systems are working. And a lot of that is working with contractors and supply chains to improve just the structure that's getting there. Because the world of converting to heat pumps is a lot more than just offering incentives. We need to, a lot of the incentives, the struggle with incentive programs in this sphere is that we don't quite have the contractor base to do it well enough to make the incentives be functional in the market. So that's a lot of what I'm doing. Today, one of the technologies that I work with a lot is ground source heat pumps. Again, I'm talking about the residential scale, tipping into small commercial, right? You know, multifamily, like that kind of world, but ground source heat pumps as a space conditioning technology. And what are the basics of it? And what are we thinking about when we install them? And what are the options with them? So feel free to interrupt me at any time. And I'm going to do my best to go. Thank you for also just dealing with this not working. I have a beautiful slide deck here that you will not see, or maybe you will if you got a great eyesight from the side. Then I'm going to try to like use just as a trigger, and I'll put a few things on the board. But I hope you're very good auditory learners, because today is going to be auditory learning style because of a technology snafu we are dealing with. All right. So number one with heat pumps, just this, I'm going like bare bones stuff, really basic stuff, starting from ground level. The key to heat pumps is they don't generate heat, they move heat. That's the only system that does this. Like all the other heating systems we have, you generate heat, you burn something, you create heat in one location, you run electricity through a wire so that such that the wire gets all hot because it doesn't like the electrons running through it. You create heat in one spot, and then you try to move that heat into the house. Heat pumps are very, very different. They take heat from one place and they pump it to another. The word pump, as much as people think that the term heat pump loses the audience because it feels weird, it's not like, you know, it's not as intuitive. There's been so many workshops to try to rebrand heat pump as something else, but they pump heat. They literally actually pump heat. It's the perfect name. I'm an engineer, so I think it's perfect. I get that no one else does. That's fine. All right. Because they pump heat, they can break the laws of efficiency without breaking the laws of efficiency, right? The unit, the energy going into a heat pump is the energy used to like run the parts, the fans, the pumps, the onboard computer. The output is how much heat you moved from one place that you didn't need heat anymore to the place that you do. And because of that, your efficiency can be above 100%. And everything else, your efficiency is locked in at 100% maximum. Right? The amount of heat you put in or energy you put in equals the amount of energy you put out if you are generating, or at most equals. But with heat pumps, you can get more efficient than that. And with ground source heat pumps, we're typically, for space conditioning purposes, we're typically talking at something in the range of 400 to 500% efficient year round. Very, very efficient. Air source heat pumps in a cold climate, 250% efficient, plus or minus, depending on the design, depending on what you do. So ground source heat pumps right off the bat have a much higher efficiency availability to them, and which makes them interesting to talk about. All right. Heat pumps are weird, but you also have like dozens of them in your life and you just never realized it. Your car you drove in here has a heat pump. Your refrigerator is a heat pump. Anything that you've called an air conditioner is a heat pump. The refrigerators out there are heat pumps. They're all using the same technology. Taking heat from one place, using something called the vapor compression cycle to move that heat to where you want it, using a little bit of electricity to squish the heat into a smaller volume and deliver it where you want it to be. So everything you're dealing with heat pumps all the time. It's not actually a new or esoteric. The difference between a heat pump and an air conditioner is a reversing valve. An air conditioner only allows you to pull heat out of your house and pump the heat from indoors to outdoors. A heat pump in a home lets you do that, or switch it and pull heat from outdoors to indoors. Either order, and the engineering that goes into to make that work functionally, that's the fun, that's the sauce. All right. There are four kind of primary flavors or forms of space conditioning heat. We're going to talk about one today, but I'm just going to mention the other forms, right? So split systems, air source split systems, they have a unit outside, a long line of the refrigerant, which is the secret chemical medium, the liquid, the medium that lets you transfer and pump the heat, do that pumping action we were talking about. They have one thing outside, a long line inside, and then a thing in, and then a unit inside that lets you deliver that heat, and a heat exchanger at each spot. So you're collecting heat outdoors, pumping it inside, you're squishing it first to make it super hot, you're pumping it indoors, then you're blowing over another heat exchanger to move that heat inside. And then you return the refrigerant outdoors and it does that again. It goes in a long cycle. But you have these long line lengths. That's a split air source heat pump system. Ductless mini split, ducted, those are all the same, in the same ballpark here, the same technology. You also have packaged terminal heat pumps. These are heat pumps that are right up against the wall. You see them in hotel rooms, right? You go in a hotel room at the base of the big window, there's this big thing. Sometimes that's just an air conditioner, but in a lot of hotels, especially warmer climate hotels currently, it's a heat pump. It's pulling air from the outside, the other side of that wall, compressing the heat in from the air and bringing in its heat. And in the summer, it is taking heat out of the room, compressing it, dumping it outside. And it does it right sort of through the wall. But in that case, you don't have this long refrigerant line, right? It's all self-contained in this little teeny thing. It's like literally this big, somewhere inside that device that is doing all that heat exchange for you, hermetically sealed, factory sealed, none of this line-like stuff, no line losses. So there's a value there in the engineering. There's a value there in refrigerant leakage. You also have air to water heat pumps. These are heat pumps that is similar to split, where not always, actually most air to waters are not split, they're packaged, but they're on the outside. They pull in air, they take the heat out of the air and they dump it into water in a box that sits outside your house. And then it pumps the water into your house, the hot water or the cold water, depending on the season. Now you have ground source heat pumps. This is the fourth flavor we're going to talk about the most today. What these are doing is they're pulling heat out of the ground. They're compressing it. They're dumping it into your house. And in the summer, they have the option to pull heat out of your house, compress it, dump it into the ground. All right. I've been very careful always calling this ground source heat pumps because ground source heat pumps are not geothermal. And this is my hill to die on, and I've lost the war. I know that, and I'm okay with it, but I'm still going to say it. Geothermal, conceptually, is heat that got to us because of the heat at the core of the earth, right? Our mass of our planet, because it's squished in the middle, generates, there's a ton of heat down below, well below the crust, 6,000 feet, 5,000 feet. Lots and lots of heat there. In a couple places that bubbles up towards the surface, like Yosemite, right? That heat shows up. Iceland, have fun. There's lots of heat there. Yellowstone, that's what I was saying. I said the wrong word, I'm sure. Yeah, Yellowstone, Iceland, right? So places where the geothermal heat gets closer to the crust because of natural geological features. Awesome. We can tap into that heat. We can use it. There's nice enhanced geothermal systems now that are better drilling technology to get us down to the deep stuff easier. There's some really fun stuff on the power plant level happening there that I won't talk about today, but I love geeking out about other times, so maybe afterwards. But like geothermal is heat that came way down, thousands of feet, and it came in a couple places on Earth closer to the surface. Ground source heat pumps, and what we're talking about, the heat source is the sun. Surface of our Earth is heated by the sun. It absorbs a lot of that heat all year round, even in the winter. And the top 3 feet vary seasonally, right? Right now, if you try to put a shovel into the ground, you hopefully not break your shovel, but you might, depending how rusty it is, how long it's been in your garage. But like, the ground close to the surface is cold right now because it's been cold outside. In the summer, the ground is warm because it's been warm outside. You get about 6 feet down, that stops. The ground is about 55 degrees Fahrenheit, year round, plus or minus 5, no matter what. Pretty much anywhere in the States, anywhere in the country, anywhere in the world. About 6 feet down, other than in Yellowstone. It's going to be 55 degrees, just a little bit below the surface. The source of that heat again is the sun. It's not the earth. So technically, geothermal only refers to heat that's being pulled out of the earth. This is ground source because it's being heat that's being pulled from the sun that happened to have warmed the ground near us. So that's the esoteric difference. I care, no one else does. And I'm okay with that. All right. Ground source heat pumps themselves are incredibly boring to think about or look at, right? So they're just a box. They're very boring boxes. Here, let me show you. That's what a heat pump looks like. That's what a ground source heat pump looks like. Very exciting, incredibly sexy, dynamic, really like, whoa, that's got a lot going on.
Nice box.
It's a small box. This box is bigger than that box because this one has a fan in it because it's trying to blow air into your house. This one doesn't have a fan because it's going to pump water into your house. Both are ground source heat pumps, but they in and of themselves look like nothing. They're very, very boring. Inside that boring is a vapor compression cycle. So I don't know how much I want to get into this, but we'll start. Vapor compression cycle is actually what a heat pump does, whatever the heat pump is, whether it's an air conditioner, an air source heat pump, a ground source heat pump, anything. It's the way we move heat from one place to another place. So, you have a source. You have a sink. And you'll have
Ask you a question while you're drawing.
can
What are the limitations to efficiency in a heat pump? And
fundamental physics limits.
yeah, I mean, you said you can break the laws of efficiency without breaking the laws. I mean,
Yeah.
what is there? Can we see a day in the future when the percentage potential in heat delivery grows, and how much from 250% here in our climate? What are the limitations on that growing?
Interesting. I mean, on like a fundamental physics level, there's a limit somewhere, but it's not not really. Right? Because again, it's the amount of energy of pumping you put into how much you can pull out. So it's going to be a constriction of power electronics on our pumps, on the how much it takes to compress the refrigerant that you happen to be using, how much energy that takes to like compress it and move it, the pumping power. I mean, so right now, the very most efficient systems that use this technology are probably like 900 to 1,000% efficient, like a 10x, like the very most in like really hyper specialized contexts, right? Where the lift is known, it's small, like, and you know, that you can, we've been in residential application technologies has been steadily rising in both in air to water, in air source, and in ground source, all of them as the engineers put more and more of their time and energy into doing this better. But yeah, there you go.
So
there's at least a ballparking.
So does it stand to reason that someday they will be a lot better than they are now?
I would say marginally better at best. Because this is, I mean, again, we've been using the vapor compression cycle to cool and heat for a pretty long time now. There's been
Talk in June is about new fluids.
new refrigerants, yes. Yeah, there are new refrigerants, but a lot of that isn't about achieving higher efficiencies. Most of that is about reducing the climactic impact of the refrigerants themselves. Yeah, that leak. So refrigerants themselves, this chemical that we're using that I'm drawing a diagram about, they have very high global warming potential when they leak into the atmosphere. And we leak a lot of it into the atmosphere. And so we're finding as we get, more and more efficient on everything else, that become of the wedge of climate impacts of global warming potential, like that wedge is getting bigger and bigger and bigger because we're not addressing it. So very recently, last year, we switched from one class of refrigerants to a brand new one that is about 1/3 of the global warming potential of the old one, at least in space conditioning applications. Because all right, and then hey guys, don't fight. All right, so vapor compression cycle. Source and a sink. We are pulling heat out of here and we're trying to put it here. So you have something hot that you're blowing or pulling or flowing. It's a liquid, it's an air, typically, across a coil of refrigerant. So this is a coil that is filled with refrigerant, which is again just a chemical. That has useful thermal properties. This chemical starts as a cool, low pressure liquid. But then when we run it through here, it boils. Turns into a vapor, low pressure vapor. Because it's designed to have a boiling point that will boil at whatever that are near or at the temperature of the medium you're trying to flow over it. In a ground source heat pump, we're flowing 55-degree water over, right? Because we pulled that water out of the ground. We'll talk about that in a second. You're flowing 55, so you're boiling some refrigerant that's gonna boil around 55 degrees, turns into a low pressure 55-degree vapor. That's awesome. That's useless in our house until we put it through a compressor. What the compressor does is it squishes it. And as we know with a pressure cooker or just holding a snowball, pressing it, when you compress something, you add heat. The heat quotient goes up. Pressure and temperature are related. There's all sorts of charts that tell you this. Physics books tell you this. We use it. We press the gas into a high pressure gas that gets very, very hot. Very, gets much hotter than 55. In these systems, it typically gets up to like 110, 15. That's useful in our house. We like 100, that lets us do stuff. We're actually 130, 140. That lets us do stuff in our house now. We then run that high pressure gas over something else in our house that we want to use to distribute heat. Again, either air or water. We can blow air over it and then heat the air and then run that through ducts to get heat where we are. That's that bigger box in the previous slide. Or we can run water over it and heat up water. We use that for domestic hot water in our bathtubs, in our showers, in our sinks. Or we can use that water to use hydronically through our house and spread heat through our house. Or we can do a second exchanger and blow air over the hot water and move that air, which is also something that we sometimes do. So you can you put a medium and then that hot refrigerant it condenses, switches instead of being a gas, it turns into a warm-ish liquid. Returns, this is an expansion valve, still under high pressure. Expansion valve releases the pressure, gets colder again, does it again, over and over and over again. That's how we pump heat from one place to another. That's it. Marcus.
Could you just talk a little bit about how that compressor works? Because it sounds like it's a really critical part of the process. And I guess I understand the snowball analogy, but I just don't quite, from a very practical perspective, understand how that works.
Like actually the physics of a compressor itself.
Yeah, what is it doing?
Most ones we have now for these applications are a scroll compressor. So it basically you're literally just squishing it. It'll be going in a loop, and the thing that's circling is oblong, like a football in one spot. You're literally just pressing it. You're just pressing the liquid around or the vapor around and squishing it. There are good YouTube videos that'll do a much better justice, but look at how does a compressor work? And this is one there's one of the biggest compressor companies in America. It's called Copeland. This is just a total aside. Copeland is one of the biggest compressor manufacturers in America. They dominate the market, or they have dominated the market as American engineering, but they've always shied away from doing variable capacity inverter driven compressors, ones that can kind of change how much they compress. And just last week, they announced they're switching into that industry. And a lot of us are very excited. Yeah.
In the simplest way as an educator to show PV equals NRT to folks and children, we set up a bicycle pump and we pump a canister up. And as we pump that canister up higher and higher, it gets warmer and warmer to touch.
Yep.
And then when we press the valve on that container and release it, it gets colder and colder. It's like any canister would to release the pressure.
All right, so that's how we move heat with any heat pump, including ground source. All right, there are so that's sort of how we get the heat in. So now I'm going to talk about this side. What is our source? Where is the heat coming from? And there's sort of 4 flavors of where that heat comes from. And then after that, I'm going to talk about this side. What are our different ways of getting into the house? So I have a rag. There it is. Okay. Oh yeah. Hold it very carefully. All right. The most commonly known one, you have a house. And you can drill down vertically. You drill a well, typically around 100 feet. That's sort of the wells that we have available. A lot of them were originally purposed for well drilling, water well drilling. If you're gonna start drilling, you may as well go all the way to 100 because setting up the drilling, getting it there is the biggest cost. So typically about 100 feet down, you have a closed loop pipe. where you run water down and you pull it back up. Sometimes they're annular, but typically it's just two pipes right next to each other. Run water down, you bring it back up. You have water that comes into the house and goes into that boring box. And then cold water that comes back out.
So are they, if they're right next to each other, are they insulated from one another?
It doesn't matter. The water, the medium, this is typically just water. Might be a water with a little bit of glycol, which prevents it from freezing when it gets closer. Right, it's cold, it's getting warmer, it's getting warmer, it's getting warmer, it's still getting warmer, it's still getting warmer, it's still getting warmer, right? We're just trying to get it up to 55 degrees. Right, if you're doing like a geothermal system, you need the production and the supply wells to be farther apart because of what you're talking about. But this, it's right next to each other.
So is there a big temperature gradient that you get with the depth, or is it
No.
more about the surface area?
For surface area, once we get that, so say that's the ground, once we get 6 feet, 55 for that 100 feet. Maybe it's 56 at the very bottom, but probably not. I'd have to look that up.
Theoretically, if you had the same length of loop, but it was all, say, at 10-foot depth.
That's the other option. Nice tee up. They're so good at this. So you could also do a closed loop system where you trench. You dig a long trench or a couple long trenches, about 6 feet down. You roll. You drop down these coils. They just loop. Got a photo of it here that'll circulate in a second. But that's that one you're drilling down and you're putting out again. Say that's the ground. That's your temperature gradient below which you're 55. So just dig down and you trench. These ones, if you need more heat than this, you can build a second well. Right? And they connect. It runs typically sometimes there's a manifold where two different wells come together. Sometimes you'll run them in series, but normally it's a manifold where two wells come together.
It
Yes.
says 55 degrees.
Yeah.
Here in New England.
Yeah,
it's
right here.
55.
55 degrees if you go 6 feet down. Alaska, 55 degrees, you go 6 feet down. Florida, 55 degrees, you go 6 feet down. Maybe 53, maybe 58, but like in the scale of heat, yeah, everywhere.
Well, you just said 10 feet down was more the norm. Put it.
No, if you dig 6 feet down for a coil, you're fine.
Yeah.
Yeah. No, I wouldn't. No, when you're doing like this kind of trenching, these sort of horizontal closed. So this is vertical closed loop. This is horizontal closed loop. They're the same thing. Closed loop just means the water I put in here just goes and goes and goes and goes in a closed cycle. I'm never adding more water. I'm never putting more water in. Never taking water out. It keeps going.
And so whichever one of these gets done is just whatever's cheaper for you to do at your house.
Exactly. Yep. Whatever's cheaper for you to do to your house. This takes more land. This takes getting access to a drill rig. This typically costs a little bit more. These both destroy your yard for a year.
Well, we already have warm trenches in our backyard called a leach field.
Yep.
And we've even considered like porting those because there's a way to extend the life cycle, the life of the leach field by diagonal ports off of it. Is there any consideration of matching the two?
You could, but it doesn't matter, right? Because the amount of extra heat you're getting off of a leach field, like, yeah, sure, that's getting a little more warmth there. But we just need to get it to 55. Like these are engineered to work off of 55 degree water. So a little more heat, sure, but I don't think there's a ton of like cascading efficiency benefit there.
Would there be cost savings or just like they use one trench and putting it?
Yes. I've heard of people doing this like in new construction, like putting this underneath the house, right? Dig a little bit deeper, run, and I've heard of, I've seen instances where someone's like digging out the perimeter of their house for whatever reason to get to the foundation wall from the outside to do water sealing or whatever they need to do. And they're like, I just dug a giant trench. That costs a lot of money. Let's roll a coil through there and collect that heat and switch this to a heat pump. So yeah, if you're going to be digging trenches for other reasons that are compatible, yes, there's value there. Because the biggest cost of these is getting that heat exchanger with the ground. Right, that's the big cost. That box, not that expensive. There's something, but it's not. Big cost is getting the trench in the ground or getting the holes in the ground.
All right, is it typical like 2 or 3 holes for like a residential home?
1 or 2 is more typical than 2 or 3.
Yeah.
Bigger home, bigger load, and we're gonna go into a little bit about well field design, but yeah, bigger needs more, but like for a small 1,500 square foot, 2,000 square foot, 1 well is probably sufficient.
Is it in the scope of your talk tonight to say something about taking heat from your wastewater pipe before it gets to the septic?
Those exist. There's some heat recovery showers that pull that heat and recover it. Not my scope tonight. No. Move.
Sorry, I missed one. I was still positive, but you're drilling a hole, put it soil down, grounding, and you're getting it effective. Conductive heat
Yep. From the soil.
Subsoil or the rock or what?
Exactly. Conductive heat from the subsoil and the rock. Yep, that's it. Now I'm going to talk a little bit about well field design, a teeny bit, where it matters what kind of rock it is, and it matters how much water is amongst the rock, or what kind of soil it is, like what is the soil down there. They have different conductivity and they have different recharge potential. And I know Dartmouth's dealing with this a lot, dealt with this a lot. Like when you have a brine field, we have water that's flowing through something, it can recharge ground really well, but you got to be able to trust that it's going to be there. Whereas if it's just like a granite or a harder rock, you don't get, the recharge is conductive, which means the heat has to wander through rock, and you'll get local cooling right next to the borehole. Right? That's expected, but that's calculated in.
If the system fails, say like tree roots.
The failure rate, yes, you don't want these right next to trees. Tree roots can mess them up, but most of the history of these things last 100 years. These don't break down very easily. This is not like what this box is going to break before this breaks in 99% of the cases.
Are those wells cased? Or do they go down uncased?
I don't know enough to answer that question.
So, but you have a 6-inch hole and you're running a pipe, 2 pipes in it. Is that right?
It's built and it fills with water sometimes, like naturally, or
Again, I don't know enough, so I'm gonna pull back. Other than knowing that it's a hole drilling down into the ground and you're pulling heat out of the ground, the exact casing of it or grouting of it or like making that, I don't know enough to answer the question, so I don't want to get ahead of my skis.
Well, you're not pumping the groundwater up.
Not the groundwater. No, you're pumping closed loop water that you have charged the system with, and it's not a high volume because these pipes aren't thick. Right, a small medium volume of water that you've put together and you've done for this purpose that just loops. So you just need
antifreeze.
Yeah, often with a little bit of glycol, a little bit of antifreeze, so that as it gets to the surface area, it doesn't freeze up anywhere. Right, if it's paused for a couple of days for whatever reason, or a few hours, it doesn't freeze up in local spots. But all right, option number 3, open loop, sometimes called pump and dump. So you have a pond, you have a river, you have some other source of water, and you're pulling water straight out of the pond, and you're pulling temperate water out, and you're dumping slightly colder water back in the heating season, cooling season, reverse those temperatures. Right? You need to have a filter on your pipes so the water that comes in isn't too sooty. These ones do sometimes break down the machines a little bit faster if it's done poorly because of the silts, but pump and dump, way cheaper, right? I'm not drilling squats. If you have a pond available, if you have a river available, you can pull this off. This is a great way to save. So if you have a local pond at your house, it's close enough. Open loop.
You have to, are the pipes still 6 feet deep?
No, because they're not sitting on the surface of the pond. That's an ice rink right now. So the water's coming out from at least 6 or 10 feet into the pond.
Okay.
But as you know, with any, you're hanging out on ponds, you're walking on 3 inches of ice, maybe 6 or 8 this year. And then below that is a 55 degree, 40 degree water, right? Again, that's typically a colder source in the winter, but the system can handle that. It can pull heat out of that water, right? Pulls it out at 40 degrees, dumps it back in at 35, right? And loops that forever.
And this is the heat pump itself would be the same unit for both of those?
Yeah.
It's just changing what?
Yep.
Sources.
Yeah, they may because of the inlet temperature of the source is going to be typically colder with a pump and dump in the winter. There might be some things that you do, but it's going to be the same, and they'll just tweak the settings to be. I'm doing this as an open loop, and it still is just that same box.
But you're gonna have to have those pipes down deep enough, because
Yeah.
you can't use antifreeze.
Yeah.
And you're just.
Yes, you're not using any. Yeah, so that water's got to come close enough to your house that it's not going to freeze on the way to getting to you. Right. Again, if it's moving, flowing water doesn't freeze very quickly. Right. So. And the people who set these systems up, which is not me, they know they have all sorts of rules of thumb to prevent that from happening. Like they know what they're doing, of how close you have to be, and how maybe you have to trench some of those pipes, but how to get that. But open loop. The fourth one, which is much less common, the least common of them all, it's called DX or direct exchange. And this one they'll drill 5 or 6 10-foot lines, kind of a radial pattern like that, and they're running refrigerant straight down. So instead of running water as the medium, they're sending your refrigerant down. So the refrigerant itself directly DX is direct exchange, directly exchanging to the refrigerant rather than having the secondary heat exchanger happen when it gets this. And those take a very small footprint. That can be done in your back, small suburban backyard. And they take very little ground space. But again, those ones raise all sorts of concerns about like, what if I leak? What if I know, right? You're literally running your refrigerant pipes. Busting a water pipe with some glycol, environmental catastrophe, fine. Running refrigerant and dumping that in the ground a little bit higher. But there are a bunch of companies doing this and it can be very effective. That's sort of the fourth way of.
Is that called waterless?
Sometimes it's called waterless. Yeah. Direct exchange or waterless are the two terms that I've heard. So
It still has a loop.
yeah, it's gonna, come into a manifold to sort of pull all the refrigerant. It'll come out. So a manifold just splits refrigerant, goes down the 7 or 8 small pipes, comes back all together and goes into the house. Right. And then inside the house, then that moderate refrigerant goes through a compressor, becomes hot, gets delivered to the house, comes back cooler. Again, I'm talking all heating season. Every time I say it comes back hot, like you can reverse that in summer.
So, sorry.
Yeah.
To clarify, but the first 3 options, that water that heats the refrigerant.
Yep.
In the compressor. Yeah. There's still refrigerant in that compressor.
There's always refrigerant in the compressor. Right. So again, one of the things I said that's nice about these is that the refrigerant in the compressor is all factory sealed. It's inside that box. The refrigerant portion is like this. It's tiny. It's like a football or a helmet size, and it's totally self-contained. This again, we're talking about piping, pipe connections. Don't let it leak. Right? Can it hold pressure without leaking your refrigerant? The same kind of concerns we have with refrigerant leakage in the air source heat pump split system.
What about the efficiency, like the energy transfer efficiency of that one extra transfer?
I don't.
Water to
There's a benefit there because you have one less sort of step.
Yeah.
But it's not. I don't think it's particularly. I don't know enough to say it definitively. Like it exists. I have not heard direct exchange people like touting that as a huge value add. Right. Maybe it's like line 7 on their these are the things that make direct exchange awesome. They mostly talk about the land space. I can do this without that's what they're pressing when they're trying to sell these systems. You don't need the land. So there may be a small efficiency benefit because you're gonna have one less heat exchange to occur, but I don't think it's massive. All right. That's getting the heat out of the ground. Those are kind of the 4 core. All right.
Can I ask real quick?
Yeah. Perhaps.
If there's something that prevents us from doing that configuration, like the DX configuration as we've drawn it with water and still
Drilling. Drills are designed to go straight down. A drilling rig, that's what it wants to do.
So how is the direct exchange then installed?
They have different drilling rigs. They're not trying to go as deep, right? They're not trying to go to 100 feet. They're not designed. They're going to go 15 feet, 10 feet, I think is the norm. I'd have to look that up again, so.
I can add a little there. There's a company, I wanna say it's called Celsius. And they are doing that kind of conical design. Eversource just put in a set of them in northern Massachusetts. Where they kind of had some constraints in space and were trying to really create a dense set of wells. And they are able to do that type of drug.
Okay.
But more like the first design that he drew, kind of deeper.
Yeah.
Substantially
Okay.
deeper
Yeah.
wells.
Yeah, so the standard well drillers are set up to go straight down.
I guess my question is like more about like what's being run through the limits, you know?
Okay.
Could you, like, why would you run your refrigerant through the direct shade because it leaking versus run water through that?
The amount of earth you are accessing with that conical drill is small. And the water, you're not gonna be, and the time that the water is going through it is shorter. You're not gonna get it up to that temperature. But the refrigerant is gonna absorb a lot more.
So that like offset that, like that whole question there about that extra shade.
Yep. Yeah, and then you also lose that removal that's gonna change too. Alright. So we pulled heat out of the ground, we've squished it with a compressor, and now we gotta dump it in our house. The fun thing here is that like literally everything you've ever thought about that heats a house is an option. Right, so ground source heat pumps are incredibly adaptable to the various ways that we heat our houses. Right, so you can heat these, you can run air across the refrigerant coil and duct it. So ducted air, forced air, hot air goes through your ducts, goes into all your rooms. You can put that heat into hot water, make that water hot, run that through hydronic piping. And hydronic piping can be baseboard, it can be floor, radiant. Hydronic piping can be with a fan coil blowing over the hot water to move the air, move the heat even further into the house, or even into a ducted system off the hydronic. You can do all these different things. You can do ductless, where you run either the refrigerant itself. Again, this breaks that rule of contained, but you could run that refrigerant to a ductless unit. Right, just like a ductless, and there's systems that do that, where they run the refrigerant up to the upper floors and it goes into a ductless head, and you blow air across the refrigerant up there, and right, and return it back to the system. Again, that's a split system where you got to run that line and charge it with a refrigerant, but these are being done. You do a hydronic ductless. You run hot water to a ductless head, blow air across the heat, the water right there. You blow air, you have hot air coming into your room. So you really have like a lot of different flavors of getting this heat into, around, and through your house. So the other thing we have, the challenge with all heating is just like the distribution, right? Getting heat everywhere that it goes. But ground source heat pumps are very dynamic that way. They're very adaptable. So some of these are water to water heat pumps. Some of these are water to air heat pumps. Those are kind of the terms that get used, right? If it's water to water, I'm taking the water I pulled from the ground, exchanging it to water, domestic water that I have an internal pipe for hydronic piping. For distributing.
Just
Yes,
confirm, these heat enough, they provide enough through the compressor to heat large houses,
yes. Yeah. Very much.
just like air.
Yep.
Air heat pump.
Yeah, so like the largest capacity, like there are 80,000 BTU ground source heat pumps, right? There's 100,000 BTU ground source heat pumps that you can buy for these for very large, high heat load houses. Most houses typically only actually need 40 or 50, and we've been steadily lying to ourselves about how much they actually need. That's a different talk that I've probably given at this event in earlier days. But like there are very large ground source heat pumps where a single system can serve the load of a large house. Whereas when you're dealing with air source heat pumps, kind of the largest systems we have are about 60,000 BTUs, maybe more like 50,000 at our outdoor air temperatures. And some bigger houses, you might need at least 2 of them to serve the entire need of the house. These ones typically you can buy a box that serves the need. Now again, you then have to deal with your ground loop to make sure you have enough ground exchange to pull that same amount of heat. Right? That's the advantage of an air source is like the air is infinite around us. I just keep pulling more air, whatever that air temperature is. Ground, I gotta plan how much heat I'm pulling out. So I pull out too much heat out of the ground too quickly, it doesn't recharge, right? Pulling heat out, heat goes through the soil at a certain pace, and I'll cool off the local bore well. And I will no longer be getting 55, I'll be getting 45, 40, 35. And boom, now your 400% efficiency plummets and dies. So that's the thing that we're going to be fighting against on ground loop design.
But that's easy to remedy with good planning, right?
Yes. Yeah. Good planning, but that's the key term. And you know, that and the glitch, right? Is that good planning? Okay. There's also a little sub value with ground source heat pumps is that they can also provide your domestic hot water, either in full. Right, they just take a secondary loop off of it and they heat your water tank at the same time with a dedicated hot water heater. Sometimes they'll do that with like a second loop that's just for the water heater. Sometimes they'll do a valve switch over. Then there's also a concept called a de-superheater, where they're basically just siphoning off. It's typically in the cooling season. They're siphoning off a little of the heat that you pulled out of your house to do air conditioning. They're siphoning off and dumping into your hot water tank. And it typically doesn't cover your full load, but it supplements your load. And it's dependent and variable how much heat you get related to how much air conditioning you're actively doing. But that heat that you're pulling out of your house to cool off your house, instead of dumping it into the ground, you can use the de-superheater function from the ground source heat pump to put it into your domestic hot water and supplement whatever else you're heating your water with, be that a fossil fuel boiler or a heat pump water heater.
I've seen these ground source heat pump boxes that are themselves a supplement to an ERV system. So like 475 is selling this, where it's like, so an ERV is like heating your incoming air with the air that you just spat out your house. And in the dead of winter, sometimes the incoming air is still a little bit colder. But there are these systems that are, I think, a little less powerful and less expensive than the ground source heat pumps you heat your whole house with. All they're doing, it's like dedicated just to preconditioning the air that comes in through your ERV.
Okay, that's cool.
Yeah,
good for them. All right. Some of the challenges when we're dealing, so I've painted a pretty rosy picture of this free heat that's living under you at 55 degrees. You can pull up, you can heat your house, you can heat a big house, you can heat a small house, you heat your hot water, you can cool your house, you can do it dynamically with all these distribution options. But there's some challenges too. Challenge number one, it's expensive right now, right? Whole house system for like a typical residential house, $40,000 to $50,000 installed, right? That's drilling, setup, the box, the piping, commissioning, everything. That's a pretty expensive heating system, right?
What's the operating cost for putting in fossil fuel fired system?
Operating costs are a lot lower. Depends on what fuel you're comparing yourself to. But at 500% efficiency, right, we're looking at probably 70%, 60% cheaper operating cost than oil or propane, ballpark. And maybe 20%, 30% cheaper than natural gas for people that don't live here, but live close to natural gas pipelines. Whereas right now for air source is still cheaper than oil and propane, but it's now like 15, 20% margin. It's not as big as it was a couple of years ago. Prices have changed on both delivered fuels and electricity. And against natural gas, it's more expensive to run a heat pump relative to natural gas. So those in the cities, again, not us, but my world, I work in those markets, right? We're at a price disparity in the wrong direction right now for thus trying to press heat pumps in natural gas territories. All right, so they're more expensive. They require land access, right? You gotta have land. So again, urban environments, cities, you can't just turn that apartment 5B in that building into ground source heat pump, right? The whole building would need to, right? So it takes land access, and that can be again, direct exchange reduces that. Vertical drilling makes that a little bit less than the horizontal or pump and dump, but it takes land access. Luckily, like where we are all living in the Upper Valley, most people who are owning homes or even renting homes, like there's enough land around our houses. We are spread out enough up here, even in our more dense cities, you know, White River and here, and that most property lots have enough land to do one of these solutions. I said earlier, installations are really messy, right? Like I have heard so many sob stories about people got so excited to do ground source, right? They invested in it, they are in it for the climate reasons, they're in it for the efficiency, and then their lawn was just wrecked for like 3 years to recover. The drill, you know, if you're trenching, you're just digging tons and tons of trenches. You just got raw soil, right? You're drilling, they end up being mud pits. It's just, it always trashes your lawn. It's reality. It's a shame.
So how long is a typical residential trench?
Don't know. Again, if we're talking, right, if the typical residential well is 100 feet down and back up, then you probably want about 100 feet of trenching, right? Similarly. And the layout of that and how much of that ground is like talking to itself for like how long you go versus looping back, that's in your well design. So your bore field design of like, or your trenching design, or how much heat, you know, how much heat you're stealing from that land versus not. I have a couple, we'll do a photo exchange again. So this is like what it looks like to, like that's drilling, that's trenching. It's like, you know, it's just sloppy. It's just not. No one's like, oh, I'm so glad that I did this. And you recover, like grass grows, you know, like landscape is possible, but just if you're thinking about doing this in your house, go in with clear eyes. You're gonna be upset and angry and annoyed at this reality when it's all done.
You know, but a lot of us have fields, you know, that we
Yeah.
just mow, you know, once a year, so what's the big deal?
Yeah, no, some people it's like no big deal, but just I you know, I don't want to get painted like, and this is of all the things, all the problems in the universe, this is not close to the top of the list.
It's easy to fix too.
It's fixable.
Put that cost into your evaluation.
I never want to go into a group saying ground source heat pumps are awesome for all these reasons, and then like that hits. Like know that that's going to be part of it. That's okay. All right. And then the third challenge is loop field design. So we've talked about this a little bit already, right? So when you're pulling heat out of the ground and out of the ground and out of the ground, again, we're talking about how well does that heat migrate through the soil, through the rock, whatever's down there, get to where your water pipe is going. And heat, just like rock, like any material, has a certain amount of conductivity of how quickly heat can flow across it. So if you keep pulling heat out of the ground, out of the ground, and out of the ground, you will get drift. And every system has drift. Typically, they plan for a few degrees of drift, but then it kind of hits this asymptote. And it kind of holds. And like the amount of heat that can come from far-flung areas or a little bit deeper in the earth or whatever it is, like that pace that you get a temperature gradient from right next to the bore to 80 feet away from the bore, that is a big enough temperature gradient to be driving conductivity because heat doesn't move conductively unless there's a temperature difference from point A to point B. So you build a little bit of a conductivity at 3 degrees, 4 degrees, you pull then that heat's flowing at the same pace that you're plucking it out. You have to plan for that. So how close are your wells to each other? If you're doing loop field, how tight is that loop field? And there's all sorts of software that just does this for you. You tell the conductivity of soil, you tell it your plan, and it says, you know, drill 2 and make sure that they're at least 30 feet apart or 20 feet apart. Or drill 2 and 10 feet apart is fine. Because yeah, you're gonna really cool off that area, but we can work with that. We're getting enough heat out of the system.
So if you have enough land, doesn't it make sense just to go 100 feet out into your field?
Yeah, again, the damage of doing extra is cost. Right? Or the negative of doing extra is cost. But you got the excavator out there, you know, so typically, like, yeah, those that are doing trenched kind of just like put in a buffer, like put in a safety factor or two. Because I got the excavator out here, I'm digging anyway. Right, it's piping too, right? It's a few things. But yeah, if you got the land, you got the space, you got the excavator out there, the incremental cost of going a little bit too far for a safety factor. Drilling, sometimes, especially if it's a step function, you're right, like 100 feet, I need 120. Right? Like, do I go that second, you know, do I bring, but you know, that's a huge extra cost to move the well, drill, you know, to drill the second well. So, but that's the planning stage of like, you gotta, you know, your soil conductivity, You got to know what you're getting into. So I consulted with what's the name of the library in downtown West Lab? K something, Kilton had the ground source heat pump well. They sized it for a certain load. It wasn't the heating load of the entire building because in the time that they did all the drilling, which is all underneath the parking lot, they didn't think the technology was up to speed to cover everything. So they did like a sort of a semi. They like wanted it as like a partial, as like a reduce the load, cover some of it, and then they started operating it full bore. And they have a massive temperature drift, and they're getting return temperatures of like 32 degrees, sometimes like 34, 35 coming out of their wells because they have cooled off the ground directly below that parking lot. And it's not recovering fast enough because they didn't. Now that one, they planned for a certain use case and then they did a different use case. So that's on them, but they also didn't think about it when they started using that second use case. And so they're trying to figure out ways of like, okay, what do we do? Do we drill more? Do we go back and expand that? That's very expensive to pull it all back up, redesign the manifold all the way that those pipes connect, right? Versus supplement with air source heat pumps, stop trying to pull as much of the heat out of the ground. The other option is recharge the ground more. They aren't using the cooling side of theirs at all. In the summer, if you are cooling, you're dumping heat in the ground, right where you want it the next winter. So there is like an ebb and flow and a yin and a yang there. So as cooling loads get higher, so that's what earlier I was like, you can siphon some of that heat off to use for your hot water. Depending on your system design, you may not want to do that. You may want to take that heat and put it back into the ground so you have it available to yourself next winter. Now around here, our heating loads are like 3 times our cooling loads. So you're never going to be fully balanced. You're still going to get like a little of a drift, but you hopefully get to that asymptotic point where you're not drifting any further. You're still getting useful water temperatures out, and your recharge of the ground in the summer is like a nice little bonus for efficiency.
So one of the things you mentioned is like that depth of like 100 feet to 120 in a well. So in Hanover at Dartmouth, our wells are going to be about 800 feet. The first 100 feet is going to be like an unconsolidated sediment, basically soil and dirt. And our bedrock's at about 100 feet.
Okay.
And I guess I'm just wondering, like in a residential setting, where you probably don't have the benefit of being able to drill test wells, which is how we know where that bedrock is. How should people be thinking about that like trade-off, right? Because the trench approach has the same challenge. So you going along, you run into a massive heap of bedrock, right? And now all of a sudden the cost of that skyrockets. Similarly, you're drilling and you run into a massive boulder or you run into your bedrock. The drilling technology that you're going to need to use to get through that may or may not be something that they have on board with their particular drill rig. And so I guess I just wonder, how do you help residential users like make that trade-off or help them decide how to handle that situation?
This is part of what makes these costs higher.
Yeah.
Right. So like customer A, soft soil, 100 feet, high five, thanks for my $50,000. Customer, I made a ton of profit. Customer B ran into some bedrock, ran into some crap, had to deal with it, lost money, but I made it up a customer. So the pricing doesn't typically change much, but this is that's the dynamic of, because you don't know going in.
Is there well drilling? Is there like well drilling history versus sonar or other kinds of
I do not know enough about what's being like in the residential kind of like 100-foot well. I don't think there's a lot of innovation going on with drill bits and sonar and some of the other things that we're doing for like enhanced geothermal for like power production. But there's been a ton of work lately on that maybe will trickle down to some value. And typically with like this kind of drill depth, we're kind of going old school and dealing with pain points when they show up.
That way, like maybe a fixed price contract is actually a more reliable approach if you're doing this. Because then regardless of whether you hit bedrock at 30 feet or 50 feet or 100 feet.
De-risks you.
As a consumer.
Yep.
It's on the driller.
Yeah.
I guess I'm just surprised about the temperature, right? Like air source heat pump works pretty well efficiently down to like 34, and then the efficiency drops off, but like down to -15, and still like.
Oh yeah, they're still churning.
I guess I'm surprised that like the ground source can't just get more latent heat out of something that's even like 30 degrees or whatever.
A lot of that is that the compressor and like the way it's designed, it's designed to be optimized for this very consistent lift,
Gotcha.
right? I'm designed for 55 or 52,
Yeah.
right? And that's what I love. And I'm really efficient when I go from 52 to 130. If I start trying to go right where the air source heat pump is designed for this world, this range, right? And it's like I can do really well at 45-degree air. I can do okay at 30. I can do still fine at 10. I start to work a lot harder at -10, but I can do it if I have a variable. So again, the ones that do that, the cold climate heat pumps, have a variable speed compressor. These are single stage compressors, right? They have one speed. So it's cheaper for the compressor, but you lose that kind of I can adapt to my reality that you get out of an air source heat pump.
Also much less efficient as you get lower, so.
Yeah.
The amount you save in 250
Right.
at 0 degrees.
Yeah.
250%.
Yeah, typically around 0 degrees, most of the better heat pumps are more like 150, 100 at best, around 0, 175, some of them. Right, but seasonally, across the winter season, 2.5 in a cold climate is about. Sometimes, again, that's actually maybe lowballing. I see a lot that are in the 2.8, 3.0 range sometimes now. Some of the studies coming through for air source that are well designed, but.
I want to throw a wrinkle in that in just a second.
Yeah.
But I'm just going to back up one click here. White River Junction and the Hartford Energy Commission, Dana had to leave already, but Tad, who's usually here, and I and Dana hang out with the Hartford Energy Commission,
Yeah.
non-voting members all the time. We've been working for a couple of years on a potential geo-exchange system for downtown White River Junction with Oak Ridge National Lab down in Tennessee. We had them look at our core samples. We drilled somebody at the courthouse here a couple of years ago, and then had them do the analysis of the whole thing. They came out with a sweet spot around 500 feet. We've been following Marcus and the whole gang at Dartmouth very closely, and Princeton as well have done this kind of thing. We were very, very gung ho on geo exchange, ground source, we have a park and everything. We're ready to drill, but there's been a very recent technology change she just touched on, which is that air source heat pumps tend to be calibrated around the compressor at a certain temperature range, and that's what the restriction is you can't go, take over above a certain temperature and below a certain temperature before you start to drop off the efficiency. But you can move that temperature range when you build the machine.
Yeah.
So there's a new trick out called multi-cascading systems.
Yep.
And this allows you to set the range. The analogy would be we're dealing with a waterfall where you've all of a sudden a little bit collect, you just splash down over the waterfall. This is more like a system of locks where it starts small and it goes to the next lock and the next lock and the next lock. Depending on what the temperature is at the moment, the system gets that particular part of it and uses the other pieces along with it.
Different compressors?
Yeah,
There are four
different compressors for
And
different
so-
stages.
so
Stage
it-
compression.
There's a company in Western Massachusetts called Fluid Technology. It's FLOOID. Okay, and Tad and I just spent a couple hours on the phone with their chief technology officer last week.
Fluid is fun.
Fluid is fun, and this thing, they claim that they're going down. I think it's like -10, -20, whatever, up to 113 Fahrenheit. And it's the range, and they're holding most of the efficiencies throughout that. The whole unit for like a smallish house would be about $9,000, but you save about $18,000 for the drill for the well on the whole thing. We're enthusiastic enough in White River that just in the back of the napkin, we're starting to think about replacing our drill field idea with this for some of the big commercial custom units. It may cut the whole drilling part of it out of it. And they're talking this being commercially available next year. I mean, that's the speed this is coming on.
So that's an air source?
It's an air
Yeah,
source.
fluids, air source, multi-compressor cascading.
Compressor, and it does the same thing, but it just leans on whichever side of the unit that the temperature range you're on. And but you get rid of the wells. The wells are kind of cool, but for White River, for example, we were looking at the government calculated out for us 500-foot wells, which is about the limit. If you're going to go drill 500 feet, beyond that, you're in plenty of the Bureau of Mines territory and special permits and pipes break down because of gravity and everything else. But I just would point out that multi-cascade one may be the holy grail here.
Yeah, so I'm tracking fluid, obviously,
Yeah.
right? Multi-cascade, cascading heat pump systems have been around for a long time, right? Again, this is you have multiple compressors, I take the heat from this to this, and then I do it again from this to this, then I do it again from this to this, right? Each one has a heat exchange, a little bit of loss there, but you're able to get this bigger lift. And you have this variable lift. You can also be like, I can skip those first two. I don't need them. I'm only going to go to stages 3 and 4 because the inlet source fluid is already there. So I can ignore these ones that were meant for the coldest of the cold. And I can just do the steps 3 and 4. That's what Fluid's kind of doing with their engineering. It's awesome. Historically, until Fluid kind of came on the scene, it's been too expensive to consider for like a residential application. They are claiming and attempting to break that mold, and we'll see how they do. And any other engineering firms that are breaking into the space. So, all right. Talk to some of the challenge. Oh yeah, please go ahead.
How about an old system which was a fuel oil boiler? Converting that to ground source heat pump.
So if you have a boiler, right, you're boiling oil, you're creating hot water, you're spreading that through your pipes.
The boiler's dying.
Yeah, boiler's dead. Yes, you could move in one of those boxes, the smaller of the two, drill a bunch of holes in your yard or trench and set that up. Yeah, so that the distribution you have in your house to move that hot water to heat your space, whatever that is, could be used by these heat pumps.
I was told that it's a different type of heat exchange, or not heat exchange, but the radiators are different.
So it depends. So yeah, this does focus. So most baseboard hydronic, which is those like those radiators that run along the base of so many of our rooms in New England.
Yeah.
Those are typically designed to use about 180 degree water, 180, 190 degree water. And if you have 190 degree water coursing through your 10 feet of baseboard or your 30, whatever it is, someone at some point did either a calculation or went like this and said, that's how much distance of copper with 190 degree water in it I need to heat this house on the coldest day. Ground source heat pumps are going to be happier putting out 140 degree water. They can go higher. There's an efficiency penalty when they do, but they can and they will with what's called an outdoor temperature reset. They'll go up to that 100. They'll typically stop at 170 or 108, not all the way 190, but they can supply that enough heat to use those same baseboards in most cases. The other half of this is that most of those baseboards, when that person did this and said, I need 20 board feet, I need 15 board feet, it was a total guess and they have twice as much as they need. And if you course 140 degree water through it, you're fine. You're just fine.
What would someone do if they do that for heat? How would they get cooling out of the system?
That you don't have the option for cooling unless you do some kind of, because condensation, you run cold water through those pipes, they're gonna get coated with water, drip all over the corners of your floor, you're gonna rot out your house. Don't do that. That's a bad idea. So if you want to use a hydronic system for cooling, you typically have to go to some form of hydronic ductless fan coil, like hydronic fan coil, where you're blowing air over a dedicated cold water loop. And that's what's getting your cooling in. That you can duct that, you can put that in just a couple of rooms, a spot cooling for like the center of the house or your bedroom, where like a couple places you want air conditioning. But otherwise you'll need to and that takes more, like you can't just tap it, that's like a totally new distribution system dedicated to that cooling effort. Or you switch to a radiator style that has a drain pan for the condensation. Right. But also cooling doesn't like radiate into the house as well as heating does because of temperature delta. But yeah.
No.
Yeah. It's like my 50 degree, my 55 degree radiator of just like cold water pipes is not like getting cold into my space nearly as well as my 130 degree hot water is bringing heat to the space. All that's because the temperature delta between what you want the air to be and what the medium is much bigger on the heating side. So typically you want to do something with a fan if you want to get cool. You got to blow air over something eventually. So you can blow it over a cold hydronic pipe or you can blow it over a cold refrigerant. All right. A couple other, going back to some benefits. So between air source and ground source, right? So those are the two main technologies we're talking about when we're trying to switch our homes to heat pumps. Ground source has much better peak efficiency. again, so we just had multiple polar vortex events here, right? You got darn cold, right? And those air source heat pumps, they were working hard, right? I mean, mine chugged through the night. It got down to -30 a couple times, and they made it. They were working the whole night through. House was fine. House was happy, but the efficiency plummeted during that peak. They were drawing the max, whatever kilowatt they're rated for for hours and hours on end. Whereas ground source, your peak loads are not nearly as high. So utilities love this. The utilities hate peak loads. And right now we're still a summer peaking grid, but we know that in the 20 to 40 year time horizon, maybe 10 to 30 year time horizon, we're going to become a winter peaking grid. The utilities are paying notice. So they are thinking of that peak dynamics to them. So they're trying to push ground source over air source in some instances, because for them, it's a better long-term, it's lower peak loads. It also has more of a chance to load shift, which means they'll pause for a few hours at the peak and then turn back on when the peak subsides. So utilities love that as well for load flexibility. They're great for cold climates because people in this room are typically like eco-conscious energy geeks. Thank you. I love you. You're my people. But general public at large are very skeptical of cold climate air source heat pumps to actually work in our coldest of temperatures, right? Everyone's like, you need a backup. Go get your heat pumps and make sure you don't turn off your furnace. Have your furnace, your boiler always there. You're going to need something else. They don't work when it gets below 0. They don't work when it gets below 10. They'll pick some other number. But there's a lot of angst about the capacity of cold climate air source heat pumps to be the sole heating source in a house in our climate. All that angst is wrong if you design it right, and I have proof. But that angst is real, and it's in the contractor's hearts, and it's in the consumer's hearts. This absolves all of that. So there's that value.
And the grid's got to build for it too. Now, 50 years ago, there were utilities that would pay you to get rid of electric water heaters.
Right.
Brag about that because you can't put that demand on.
Yeah.
And now everybody's, getting urged to put it into split systems. It's not like 3 years ago. It's great. We have our baseboard system, which is also great. When it's really cold, I'm running that because it's more efficient.
Yeah.
Price wise.
Yeah. There's an economics switch somewhere.
And it's kind of like sideburns and, I don't know what else, but it just depends on what you're talking about. So,
right.
So what are we gonna do when everybody's going to split systems? Other systems that are run by electricity. Where are we gonna get that electricity?
Batteries.
Well, you're gonna store it with batteries, but you're not gonna get it.
Fair enough. Yeah. Right. That's a different conversation for another day. But yes, I hear it. You're right.
I'm with you.
Totally.
And excuse me, and one other point I'm sitting on. 50 years ago, there was a company in Morrisville, Sweetenburg, and they were selling groundwater heat pumps, and I almost bought.
Yeah,
50 years.
Yeah, no, this technology is not new.
It's European technology from 100 years. Wow.
Technology is not particularly new. All right, so better efficiency, better cold climate performance, less of this fear of I can't manage the winter, just makes it more consumer friendly, contractor friendly, this sort of sense of guarantee. Better capacities at the cold temperatures, right? Because to get heat out of -25-degree air just takes a lot more. You just can't pull as much heat without having engineers the system for that condition. But that condition is so rare, you wouldn't want to engineer for that condition here. You want to engineer for the normal condition, primarily to get your seasonal efficiency. You hurt on both efficiency and capacity. Manageable, doable, but it's hard. We talked about the superheater. You got a question? The other one?
I'm just gonna throw out one quick technical point. That's how I roll. One of the things that kills the efficiency of heat pumps as we get to lower temperatures is actually a conservative design flaw that's being used by everybody right now, which is that what will murder a heat pump or it's the same problem with steam impellers and boots and stuff, is that when you turn to a vapor and then it comes back into the system as a vapor, you have any condensation in there, you may as well blow a shotgun or a high-speed shell through it to kill the whole thing. So to absolutely guarantee that never happens, the system is designed to go to the widest possible margin and keep it as vapor. So rather than tune it to maximum efficiency, it's taking the maximum safety approach, and that uses a lot of the efficiency of the lower temperatures. In the laboratory, in lab conditions, you can get the heat a lot more efficient.
Yeah.
When you get in your home, it's nowhere near as efficient.
Yeah.
That is coming out now becoming microcontrollers. So the next couple generations of these things, starting with Fluid and some other companies are working the same thing. We should see that get better just as a matter of time in the next 5 to 10 years, because the microcontrollers and the sensors can keep this thing within about 1 degree Fahrenheit or Celsius of where it should be, rather than like 30-degree range.
Yeah.
At the lower end of the whole thing.
Yeah, there's some, yeah, and I followed again and also have fun tracking that world. I think that's pretty far away from commercial, but maybe, but who knows, right? Like the right engineer picks up the right.
It's in the pipeline.
Yeah, the right engineer with the right business model takes the risk, and maybe it's coming faster, or Mitsubishi or Daikin or one of the big dogs decides to go all in, and we get, we can tap into that. But right now they're building it for, can this last 20 years outside a person's house without me ever having to go out there?
Yeah.
And so the safety factor, like that side of it, that sort of durability, it wins in the moment. Right. All right. Couple other tiny benefits, then I'm done, except for questions. Extremely long lasting, right? So like the box, 25 to 30 years is typically the expected length of the box. A lot of them are lasting longer than that. And it's also self-contained. It's not a lot of moving parts. They're pretty stable. And then that ground loop, 100 plus, right? When that box dies, just get a new box. And the new box is $5,000, not the 50,000. So maybe it's 8, but the box is not the expensive one. So you can just keep going with this. That's a huge value add. Very
hold on. What about these connections? My impression is that like part of the challenge is like those indoor units have to be matched to the outdoor units. There's kind of this cascade of like all that equipment.
Well, that's air source heat pumps that have to match.
And that's just, and so with these ground source systems, that is a distinct feature of them.
Yeah, it's one thing. Right. Yeah, because you're not moving the refrigerant.
Not right.
Right. The refrigerant's just in a helmet size, head size thing inside, medically sealed, runs forever. Right, until something mechanical breaks down, but there's not a lot of, like, the compressor works, but they're well designed, and single stage compressor, it's not variable speed. They can churn years for decades. So 25 to 30, and then in practice, some go 40 to 50, right? And some die at 15 because limits exist, like where mechanical systems fail. But like they're longer, like your typical air source heat pump, typically 15 years is the expected lifetime of an air source. Maybe you can eke out 15, 20, maybe 5 if you get lucky. Maybe you get unlucky and it dies at 9 or 10. Very low maintenance. There's not a lot of maintenance to do on these systems, right? So change your air filter if you're ducted, change your water filter if you're open loop. End of list, like we're done. Right? There's not a lot of, maybe you want to make you check that the flow rates through your pipes through your closed system are still matching what the design was, but like that's kind of none of that's hard, right? Clean the condensate drainage system if you're using it for cooling. Make sure that's not clogged. But again, this is very, very simple maintenance at low cost. Not a lot of maintenance on these things. They can go that 30 years with a very low maintenance bill. And then again, what I talked about earlier, fully enclosed, all that refrigerant is factory sealed, it's not going to leak. And so you have that environmental benefit, that reality. So that's what I talked about ground source heat pumps for residential applications. All right. Any questions?
Yeah. That last point is, they do leak. In that, I had a friend in town, just put one in,
In a ground source?
No, this is just regular air to air.
Oh yeah, those leak all the time.
And, yeah.
So it's like constant.
Like, so, but my real point is that's the worst thing about these. Is the refrigerants. Now, I know they're getting better, but they're still like 1,000 GWP, right?
The newer ones, the R410A and R32 are about 650, 700 GWP, whereas the 410A was, the old one was about 20,088, I think is the number.
Yeah.
So we're getting better.
Right.
I mean, there are a couple of natural, like, eventually we'll switch to propane as a refrigerant, which is the GWPS3. Or no, 1. GWP 1. Right now, the safety of that is still, again, these are units that are being used in Europe and have been used in Europe for 20, 30 years. It's literally propane as the refrigerant.
Well, they're even talking
Right.
carbon dioxide.
CO2 is a refrigerant. It's supercritical CO2. It's only useful in water heating applications because you need an exact lift. Every lift, you have a 60-degree lift or whatever. You have a lift that needs to be the same every single time. Not useful or viable for space conditioning because your lift is variable with space conditioning. Water heating you can do, and that's what like Sanco 2 air to water heat pumps are. Supercritical CO2 driven air to water heat pump company. Great company, make great products, but only viable for specific applications. They are trying, yeah. So we'll eventually get there. Right now, it's a safety factor for fire code. There are propane as refrigerant. So propane as refrigerant, obviously we pipe propane through our houses constantly, right? Like most of the people in this room probably have a propane line running through their basement. The differences are it's not under pressure. These are under pressure. The bigger difference, you can't add that chemical agent that makes it smell funny. So if you get a leak, so propane is odorless.
Captain.
Or captain, yeah. Propane is odorless in its natural state. We add a chemical to make it not odorless. If you have a propane leak, someone says, "Whoa, this is bad. This is a problem. I got to do something so I don't create an explosion in my house because I've built up propane in a weird closet or a cabinet that can eventually spark and burn." You can't add that chemical if you're going to use it as a refrigerant because the compression cycle will basically pitch it out.
But how much propane would you? Not talking about 500, you know.
No.
Right?
And typically this is outdoors in an outdoor unit container. That's how they do it in Europe. And if that thing leaks, to rat, recharge it.
Yeah.
Right? It's going to the outdoors atmosphere. The chance of a spark that would cause a big fire there, right? You can do spark prevention. You can do all and that's what again, those have been used in Europe. They've been in place in Europe for 20, 30 years. All the majors have systems that are ready to come over. So we're doing some experiments in places like Indian reservations that have different laws. So we can do some testing there. There's one in Massachusetts where they got like this special safety inspector process to confirm like all these extra very expensive bells and whistles, confirm no leakage and no safety issues. So we're starting to see pilots of R290, which is the refrigerant number coding for propane. They're seeing R290 projects happen at like pilot scale to proof of concept and be like, hey, look, no one died. It didn't burn us down, just like it hasn't at any rates that scare anyone in Europe for 30 years. It's a very silly, stupid thing, but welcome to regulation.
And that's a GWP of 3?
1 for propane, I believe. Might be 0.3. I think the reason 3 is in my mind is because it's 0.3. I don't know. I'd have to look it up. It's low. It's low enough. It's in the range to not care about.
Compared to 650.
Yes. So eventually that's where we're going. It likely will be air to water style outdoor unit, right? Rather than split system. They're not using split systems for propane anywhere that I know of. So, but that's eventually where we're going to go.
It's even better. 0.02.
02.
100-year GWP.
All right, there you go.
So, you mentioned that, with baseboard hydronic heating, ground source heat pumps it's not the best match because of the temperature required for those baseboards.
So, yes and no. Right. So most of the year to get most of the year is 35 degrees, right? We get these nights that are super cold. You get these, but you can see the histogram, like it's not a lot of hours. So in those hours, you might not have enough what's called distribution capacity to keep the house to temperature. Your room might drift a couple degrees, and then the next morning it catches back up, right? Because you're not losing as much heat out of your envelope in those once the sun comes up. So you may get a couple degrees of drift depending on the design. The other one, as I said before, most baseboard was over designed. You have more of it than you need, so you're running that like hot water and super hot water is fine, right? It had the capacity. And then the other one is that some of these do have boosters that can get that. A lot of times they just use electric resistance to do it. But they'll get the water to 140 and then they'll kick it up to 190 just for those 150 hours of the year that you need it.
Yeah.
And use a little bit of extra electricity in the process. Darn, but no one knows. So they're adaptable to that condition and still staying seasonally quite efficient.
And is that less of an issue if you have, say, in-floor hydronic mediums?
Yeah, because the stuff in floor is like 90 degrees. They love that shit. Right? That's very, very efficient. You can get like 600% efficient on some systems if it's all radiant floor. Radiant floor, ground source pairing is like, or air to water also does really nicely with radiant floor.
You mentioned the ground loop underneath the slab.
Yeah.
Construction. It sounds like a tempting thing to do to just like put that in, like even before you even have a HVAC system design. Just you have the hole done, just put down the pipe and PEX and then have it stub it up.
Just in case they ever want.
In case they want to.
Yeah.
Is that something you've seen?
I have not seen that, but I agree with you. Right? Like, I mean, again, you're working in construction, right? People don't like added cost.
Yeah.
Right. It's a little bit deeper digging, it's some level of PEC, it's some level, like it's just something, it's just money, right? It's like money better spent then than in 15 years being like, I'm ready to get a ground source system. What does it cost?
Right? Big cost is the trash.
But yeah, I don't see,
So I guess similarly, if you have a property where you're drilling a water well, anyways, the same kind of
well,
like the same people who drill the wells for the house.
Yeah, well, I see that paired as well. Like you're doing a water well, you got like because half the cost is getting that freaking thing there. Maybe not half. I'm speaking out of turn, but like a lot of the cost is just activating the well to show up at the property and staging it. You still have to stage it in a different spot, right? You have to plan that out. But yeah, if you were doing well drilling and you got an opportunity to pair it with drilling for ground source, go for it.
Nice.
Yeah.
So in a trench, are you putting PEX in or copper?
PEX.
Copper's too expensive.
Copper's too expensive. Yeah, PEX is fine.
4 or 5 years ago, Food Efficiency Vermont, they had some links to companies that were doing design sourcing. I called one of the bigger plumbing HVAC companies, and the person who picked up the phone had no clue.
Yep.
They had to call me back with the person in the company. So, and that person seemed pretty uninterested in doing a project for me at the time.
Okay.
My point is, are there companies around now doing this, interested in putting in this type of?
I could give you a beautifully long list of companies in New York State. Because I run some of the New York State ground source heat pump programs. I don't know the local ground source companies to talk to them, unfortunately. Ethan, do you work with anyone?
No. I mean, are you talking about drilling companies or just companies that do the whole thing or?
Well, I mean, I have a well company that's had to come and, replace my well pump. So they'd come and drill for me, but I need someone to design, like I need the designer, installer. Yeah.
Right, so the designer and the installer are often different entities, but occasionally overlap in a single company. Yeah, I don't know. We haven't done any ground source heat pumps. We've worked on some houses where some have been there already. But no, they're just generally not in the budget on the projects we've been on. But I would say that the residential HVAC design space is vastly underserved. Like very few people know how to do the proper calculations, and everybody's pretty conservative, and there's a lot of technology to keep up with, a lot of math to do. So
you could look at the New York State Clean Heat Incentive Programs website. They'll have a find a contractor tool. There'll be New York contractors, but maybe you can get one to come this far across.
Okay.
It's not crazy territorial expansion for them. Yeah. And I would also, I would have said check Efficiency Vermont's website because I know they have a program, they have incentives, but you can also just call Efficiency Vermont and be like, I've tried a couple people, they've all kind of like, they're listed as ground source, but they're not responding to me. do you know of anyone who's actively doing this, right? Because they'll have the list of who's been submitting incentive forms.
Yeah.
And who hasn't. It's like, I mean, in the New York program, we've got something like 400 ground source installers listed. But like, I know which ones are actually doing work.
Okay.
You know, so that's because I have access to the database for them. So
When did you reach out to efficiency?
This was, yeah, 3, 4, 5, somewhere
Yeah.
in 3 to
Okay.
5 years, so I hope it's a little better, you know.
Yeah, I would say just say it. Who knows this stuff?
yeah,
I talk to whoever knows this stuff, and if you keep at them, they should know. They have people here
Yeah.
in-house who present on this every year or two. They're working on it.
they're finding a contractor tool. You're gonna hit some people who listed themselves as a ground source because maybe they did one once or they thought maybe they'd like to get into it. And you just have to push through that. Or go to the efficiency Vermont managers themselves and say like, you give me a name of someone who's actually submitted in the last 6 months.
Okay. They'd probably do better than that if you really stick with it.
Yeah.
You know, they know which projects went well and which ones
Yeah.
didn't. So you know.
They sometimes will shy away from telling the public that. There's a play favorites thing that is a no-no in my industry. So
Well, interestingly, the heat pump incentives are still there through the federal government, whereas everything else recently went away.
the
Right, the ground
no,
source-
not for residential.
Okay,
Not for residential.
so just. Well, okay.
What if you claim a home office?
I don't know it well enough to know what counts. But 25D, which was the ground source one, and 25C, which was the air source and insulation and solar and everything else, both of those are dead.
These refrigerants are just wild. They boil at 55 degrees, some of them.
So, I mean, they're boiling, so their boiling point is adaptable based on the pressure that they're at.
Yeah.
So natural air conditioned, natural pressure, like ambient, whatever, atmospheric pressure, is the word I was looking for. They are 410A at least boiled at negative 33, I think.
Okay.
So you
So
pressurize
vapor, pretty legal.
Yeah.
But when it's under more pressure, it boils at a higher point. Wow, okay. Because it has to be in vapor form in order to be able to compress it.
Well, you need to switch it from liquid to vapor, right? That phase change is really what brings it, like what absorbs energy. So like as you know, if you do any liquid, right, it's getting hotter, it's getting hotter, it's getting hotter. And then it hits a phase change, right? So like when that phase change, that's it boiling. And it absorbs before the temperature goes up another tick. It absorbs a lot of energy. Right, so water is 210 degrees right as it's boiling, and then the vapor right above it is also 210 degrees, but it has a lot more energy density in the vapor.
4 to 5 times.
Yeah, like a ton. Yeah, so that phase change is where all of the like really high volumes, high quantities of energy can be stored into the medium.
So the whole loop is under pressure in this, well.
One side on one side of the compressor is under pressure. And the expansion valve, the other side is lower pressure.
Right. So I don't know so if the ground loop, the water's coming in at 55.
Yeah.
The water from the ground loop, that's not refrigerant generally in a ground source.
No, it's gonna be water.
It's just water. It's coming in to the compressor and then.
Well, it hits a heat exchanger with a refrigerant.
The water, right, and so when that 55-degree water hits the refrigerant then boils because the refrigerant was at who knows what temperature.
At some pressure that's such that its boiling temperature is right around as close as they can engineer to what that incoming water temperature
55. So then the water loses its heat, drops down to 35.
No, a degree.
Okay.
Yeah, like
but then
the outflow of the water, you maybe like it comes in at 55, it leaves at 50.
Okay.
Doesn't
But then
drop.
how does the ground under Kilton, it hits 50, it can't go lower than that. So it just there's no more heat to pull out.
Kilton, the problem is like the dirt touching the loop.
Right.
Started at 55, then it went to 53, then 51, then 49, 38, like it just kept getting colder and colder. And heat could not travel fast enough from far flow.
It's like it's still 50 degrees. It's not gonna warm it up past 50.
Yeah, you go 100 feet over and drill and dig a trench or drill a well, it's gonna be 55 again. But right there, where the pipes are flowing or dug in the ground, that soil is super cold.
So the outgoing water in a typical ground source system, coming in at 55, going out at 51, 50, and coming back in at 55. It's just approximately that range. No, okay, well, cool. This is great. Thank you.
Thanks, everyone.
I got it.
Cool.
What about the other end of this? The solar gain, before it even warms the ground. It's on its way in, passive solar, the cricket, eaters, all that kind of stuff.
What about it? Yeah, that's free heat from the sun that you can use to heat up your house and reduce your load.
Yeah.
Right, with good solar heat gain windows and and really good thermal design of your building to take advantage of the free heat of the sun during the winter. Totally. And I love some passive house concepts, right?
No need for that much heat over an exchange.
Yeah. I mean, that's what air source heat pumps are, is taking that heat, right? It's just, but it's the air temperature. That's what a solar thermal system does. I can harvest it directly. Okay, I think we're good.
We had somebody was watching from, where did they say? Rochester, New York. Thanks for coming.
Oh. I can tell you where your
Yeah, give them a list.
Right.
Vetted sources.
There's still more to go.
Yeah.
Oh.